Hi, in this video, we are going to look at a specific problem on statics that is quite interesting. This is the question of a rope wrapped around a pole. So we want to understand this situation. There is a rope that wraps an angle theta around a pole. What you do is you grab one end of the pole and one end of the rope and pull it with a tension T naught. The other end of the rope is attached to a large object. If the coefficient of friction between the rope and the pole is mu, what is the largest force that the rope can exert on the object if the rope is not to slip around the pole? So this is a question which has a surprising answer. So that's why I wanted to share it with you guys. Now, what is the situation? So there is a large object, there is a rope attached to it, and the rope is going to go around a pole. And you are holding one end, you are holding this end and pulling with a tension force T naught, right? This rope going around this pole is the key part of this problem, and you want to find out what is the force that the rope can exert on the object here. Basically, the tension on this end, what is the maximum tension? If you can find the maximum tension here, that is the maximum force. And you are pulling the rope from this end with a force of T naught, and it is going around a pole and describing an angle theta around the pole, and the coefficient of friction is mu, and the rope does not slip on the pole. Rope is not slipping on the pole. So that is the setup, right? So let's try to analyze what happens in this particular instance. So we will consider a small piece of the rope that subtends an angle d theta. So think of the center of the pole like this, and we were going to take a small piece of the rope. This angle is d theta. It subtends an angle d theta at the center. Let the tension in this part be T. Tension here and tension here is T. Technically, we can say that the tensions are slightly different. There is a variation of tension here. It will be T plus d tau. You can say it is T plus dt actually. However, the dt part won't matter so much. What we will do here is we will draw tangents like this, and you should realize that this angle, this much is d theta by 2, and since this is 90, we have this angle. The angle between the tangent line is equal to basically also d theta by 2. So I'll just draw a different figure and figure it out. So I'm saying here this much is d theta, this much is d theta by 2. And if I join this line, and I know this angle, this is the direction of the tangent, this is the direction of the tension, this is 90. Okay. And right, this is 90. So we have this angle is 90 minus d theta by 2. So this much is d theta by 2. So this is d theta by 2, right? So what I have is the angle between the tension and the vertical line here, this figure will be d theta by 2. What I have done is extended this and this line and taken the extension of the tangent line. Since this angle between radius and tangent is 90 here, and this much is d theta by 2, so this is 90 minus d theta by 2. So with the horizontal, you will get d theta by 2 here and parallel lines, so this is d theta by 2. So the tension force will have components T plus dt cos d theta by 2, and here also it will be T cos d theta by 2. These two components will get cancelled, and the vertically upwards component in this case would be t plus dt sine d theta by 2. And in this case, it would be t sine d theta by 2. These are the two forces that are towards the center. In this case also it is t plus dt sine d theta by 2 plus t sine d theta by 2. Now the thing is that d theta is small. So what we can say is that d theta by 2 is also small. And in that case, sine of d theta by 2 is almost equal to d theta by 2. So this component becomes t plus dt into d theta by 2. And since it's this term here, the second term here is a product of two really small quantities, we can ignore this second order differential quantity, and we say that it is roughly same as t d theta by 2, the vertical component. And this component is also t d theta by 2. So the total vertical component is 2t d theta by 2, which is basically t d theta. This is the total force component of the tension towards the center of the circle, right? So this is the center of the pole. The force component towards the center of the pole is coming as t d theta, right? Great. So now, obviously, this force is balanced by the normal force applied by the pole on the rope, right? The pole will exert a small outward normal force, let's call it n d theta, on the rope. This is the pole exerting the force on the rope. And obviously these two forces must be balanced. The n d theta is equal to t d theta. We can call it the net normal force over this whole portion, that is equal to t d theta. Must be balanced for equilibrium, right? Great. Now, obviously the question stated that there was friction in this situation and it was static friction. So the friction force will satisfy the relation mu times n. Friction is always less than equal to mu n, which is equal to mu t d theta. Because we just saw that the normal force was t d theta here, right? So we have friction is less than equal to mu t d theta on the portion of the rope, and it is this friction that gives rise to the difference in tensions. So we said that there was a tension here and there was t plus dt here. The friction is what is giving rise to the difference in tensions. So this is tension at the point theta and this is tension at the point theta plus d theta, right? Because the difference in angles was d theta. As the rope wraps around the pole, the tension keeps increasing because there is a friction component that is preventing slipping, right? There must be a difference in tension which is being caused by the presence of a friction force, static friction force, which prevents slipping. So the tension at the angle theta is different from the tension at angle theta plus d theta. And what equation we can write here is that t of theta plus d theta is basically less than equal to t of theta plus mu t d theta. Technically, what we are saying here is we are actually saying t theta plus d theta is equal to t of theta plus friction force, but friction force was less than equal to mu t d theta, right? So putting these two together, we get this relation, right? The tension at the angle theta plus d theta is less than or equal to the tension at theta plus mu t d theta. So obviously, if you subtract now these two tensions, that gives us the difference in tension dt as the angle is being changed, right? So we get basically t theta plus d theta minus t theta is equal to your dt is less than equal to mu t d theta. Right? Now this equation is a differential equation. Dt is less than equal to mu t d theta. This is a differential equation which we can easily solve. We get that integral of dt by t is less than equal to integral of mu d theta. Right? And this gives us ln t is less than equal to mu theta plus some constant So t is less than equal to e power mu theta plus some constant, which can be written as e power c times e power mu theta, and e power c can be called as a new variable t naught e mu theta, right? So what you are getting is t is less than equal to t naught e power mu theta. This is the equation that we are getting. So the maximum value of t is t naught times e power mu theta, where what is t naught? What is T naught? Remember that the rope was wrapped around it and one end of the rope was here where the angle was 0 degree, right? Theta was 0 degree and then you wrapped it around to angle theta, right? So here the force at this end was T naught, right? The tension by which I was pulling the rope from one end was T naught. So I can put at theta is equal to 0, T is equal to T naught. That is my initial condition. And that should give me the value of this e power c and all, right? So you can see t is equal to t naught at theta is equal to 0. That is the way we define our t naught, right? So as you increase the angle by which you wrap the rope around the pole, the maximum force on the other end, the maximum tension on the other end is increasing a lot. For example, we can take some examples and understand this behavior. If mu is equal to 1, then suppose you twist around the rope and this turn is like a quarter turn. Quarter turn, basically the angle that you turn around the rope is theta is equal to pi by 2, 1/4 of a circle, right? In that case, e power pi by 2 times 1 is almost equal to 5. So what you get is t is equal to, t is less than equal to t naught into 5, right? So T can almost be equal to 5 T naught. That is the maximum force that you might get on the other side. The tension here would be 5 times T naught possible, right? And that is just for a quarter turn. Now, if you think about it, if you do one full rope or one full circle, basically the angle theta is 2 pi, then e power 2 pi times mu is 1 is almost equal to 530. And basically, you can say that the tension on the other side would be almost less than equal to 530 times the tension at one side. So technically, just a couple of turns and you will be able to create an unbelievable force by wrapping a rope around a pole and making sure that the rope does not slip. So that was this particular problem. Let's look at another question. This is problem 2. Now here, there is a frictionless tube. A frictionless tube lies in the vertical plane, lies in the vertical plane, and is in the shape of a function as and is in the shape of a function that has its endpoints, that has its endpoints at the same height, but is otherwise arbitrary, but is otherwise arbitrary. A chain A chain with uniform mass per unit length, uniform mass per unit length, lies in the tube from end to end. Lies in the tube from end to end. Show by considering the net force of gravity, by considering the net force of gravity that the chain doesn't move. The chain doesn't. So now what is this tube? There is a frictionless tube that lies in the vertical plane. And the only thing special about the tube is that it is in the shape of a function whose endpoints are at the same height, but is otherwise arbitrary. So it's like a random tube size, random function whose endpoints are at the same height. This height or this y value is the same. Both the ends are at the same height. The function is arbitrary, so I've drawn a random graph, right? A chain with uniform mass per unit length lies in the tube from end to end. So technically you should think of this tube, and inside that you have put a chain, and the chain has uniform mass per unit length. So mu is the mass per unit length of this chain. We have to figure out what is the net force of gravity on this chain and use that to prove that the chain will not move, right? That is our problem. We don't know the actual shape of the chain. We just know that it is hanging on like this in such a way that actually the heights of the two ends are equal, right? So let's say this is the position x is equal to a, and this is the position x is equal to b. The height of the function at x is equal to a and x is equal to b are equal. We don't know anything about the rest of the chain, how it is hanging, right? So what we will do is we'll try to analyze this curve. So we'll say let the curve be described by the function f of x. Be described by y is equal to f of x, and let it run from x is equal to a to x is equal to b. A to x is equal to b. We already know that f of a is equal to f of b. The heights of a and b points are the same, right? Now, what we will do is we'll consider a small piece of the chain. Think of the chain like this, some arbitrary function. Now, we'll consider a small piece of the chain. This is your small piece of the chain. This goes from x to x plus dx, right? And we'll magnify this small portion. Since it's a small portion, we can think of it as a straight line sort of a situation. This is your x, this is your x plus dx portion, right? Now, what is the length of this piece? Length of this portion of the chain. So how do I find the length? I need the height and the base of this Pythagoras theorem triangle. The base is clearly dx. The slope of this is dy by dx. dy by dx is the slope. So that is tan theta. So if your angle here is theta, tan theta is dy by dx. So that is perpendicular by hypotenuse. So you can say that dy by dx times dx will be the dy, right? dy by dx times dx is your dy, correct? Okay. Now the overall length here of the chain would be root over dx squared plus dy by dx whole squared and dx squared. I'm just taking the square of this and taking the square of this and doing Pythagoras theorem. So this can be written as dx comes outside the root and it is 1 plus f dash square, right? 1 plus f dash square dx is your length of the chain. Let's call the length as dl. This is your dl length. Now, the mass of this portion of the chain would be basically mu times dl. So mu dx root over 1 plus f dash square. That is the dm of the chain, right? Correct. Now, obviously, the force due to gravity on this would be dm times g, and it will be vertically down. Now, which part of the force on this small portion, there will be a g sine theta part of the force due to gravity, which will be this way, right? And there will be g cos theta this way, correct? So basically what we can say is the acceleration due to gravity or the force on this small portion dl is dmg sine theta. Dmg sine theta is in this direction along the chain. So this dmg sine theta is along the chain, and if you measure all the forces along the chain, that should basically give you the net force on the curve along the chain, right? So you need to integrate this dmg sine theta from where x goes from A to B, right? That would give you the net force along the chain on the whole rope, right? Because right now what we are calculating is the small amount of force along the chain on this small dm, right? That is this value. So let's try to see what is the net force on the whole chain. So in order to do that, we will have to do this integration. So let's see what comes from there. Dm is mu dx root over 1 plus f dash square. Then there is a g, and then there is a sine theta. Now tan theta is f dash, right? So sine theta would be f dash by root over 1 plus f dash square, right? Because tan theta is f dash, means f dash is your perpendicular and 1 is the base. So this is perpendicular by hypotenuse. So sine theta is f dash by 1 plus f dash square and root of that. And notice that this gets cancelled. Right? So you end up with integral of mu g f dash dx, right? And think about what f dash is actually. And this was from x is equal to a to b. F dash was dy by dx, and you are multiplying it with dx, and mu g is there. So this is becoming a mu g dy. So integral of mu g dy from x is equal to a to x is equal to b is basically mu g. The y value at x is equal to a and x is equal to b are equal, and it is fb minus fa. Integral of dy will be y, and y value at x is equal to b is the same as y value at x is equal to a, because that was stated as the first thing in the problem. So this comes out to be 0. So what we are proving here is that the net force along the chain is 0 along the chain. The net force of gravity along the chain is 0 as long as the two ends are at the same level. If the difference between FB and FA was not 0, which means that the two ends of the chain are not at the same level, then the net force along the chain is non-zero. Therefore, then the chain would start moving. But right now the net force is 0 along the chain. Therefore, there is no motion for the chain bed. Right? I hope you understood this particular point. So it's a nice way to show that as long as your function has the same endpoint values, the y values, the net force of gravity on the function will be 0. Right? Let's look at a third problem. This is a problem called rope on a plane. Rope on an inclined plane. Now, the statement of the problem is pretty simple. However, it's a tricky one, so and very conceptual. So you should pay attention to this one. So we have a situation like this. This is an inclined plane with angle theta. A rope with length L. A rope with length L and mass density rho and mass density rho per unit length. Per unit length lies on a plane at an angle theta. Basically an inclined plane with angle of inclination theta. So I will draw a rope here. A rope is lying on this plane and the top end is nailed. top end of the rope is nailed to the plane and the coefficient of friction between rope and plane is mu. Now the question is asking, what are the possible values? What are the possible values of the tension at the top of the rope? Of the tension at the top of the rope. So we have to figure out the tension at this point, the topmost point of the rope. And this is the setup. The friction coefficient is mu between the rope and the plane. And the rope had mass per unit length of rho, length L, and it is hanging on an inclined plane of angle theta, right? Okay. So now on the face of it, the question seems pretty easy. The force of gravity on the rope downwards is rho L g sine theta. This is the mass is rho L and the g sine theta is the acceleration of gravity component in that direction, right? So the maximum value of friction force, the perpendicular component of force of gravity would have been rho L g cos theta. So friction force is less than equal to mu times n. So friction force is less than equal to mu rho L g cos theta, right? That is the maximum value of the friction force. So the basic common sense understanding is okay. The tension at this point must be such that it balances the friction and the downward force. The friction will be acting upward like this, and you can say that the tension is acting upward at this point on the rope. So tension plus friction should be equal to this. So you might say tension is equal to rho L g sine theta minus mu rho L g cos theta. And that is like a simple answer for this question. However, the problem is that that may not always be true. Now, why am I saying that? Because the tension at the top of the rope depends on how you place the rope on the plane. How you place the rope on the plane. Basically, there are multiple ways in which you can place the rope on the plane. Suppose one way to place the rope on the plane is that this is case 1. The rope is placed on the plane. Rope is placed on the plane without being stretched at all. Without being stretched. Okay. So in this case, if it is not stretched, then the friction will definitely point upwards and gravity will point downwards, which is rho L g sine theta. And in this case, the tension at the top could be equal to this value, what we already saw. However, it could also be equal to 0. Tension could also be 0 if your mu times rho L g cos theta is bigger than rho L g sine theta, right? If the downward gravity force is smaller than the upward friction's maximum value, this is the maximum value of friction force, right? If this gravity force is smaller than that, then the friction force that is actually going to act will not be the maximum value. It will just be equal to this, and therefore there is literally zero force that tension has to exert in order to keep it there. So basically you are getting two cases. Tension is either 0 or tension reaches its maximum value of this. In the case when the rope is placed on the plane without being stretched, right? However, you can have a situation where the rope was placed on the plane after being stretched. Case 2 is rope is stretched and then placed on the plane. Or equivalently, you can say that the rope was dragged up. Rope has been dragged up and then nailed at the point here. And nailed at this point, right? So either you drag the rope up or you stretch the rope. In both these cases, the friction force will actually point downwards. Friction is downwards in this case. So the tension at the top will be the addition. Tension would be the addition of friction plus the rho Lg sine theta gravity. So the tension could be actually rho Lg mu cos theta plus rho Lg sine theta in that case, right? Depends on how you bring the rope to the point above, whether you drag it, in that case friction is downwards, or if the rope is stretched, right? Another special case is possible actually here. The other special case is case 3, where rope is placed on a frictionless plane. Rope is placed on a frictionless plane and then suddenly friction is turned on. Suddenly friction is turned on. Right? In this case, the friction force is still zero. Basically, what you could do is you could change the plane and change its friction coefficient suddenly, but the rope was already on the plane. So in this case, the tension at this point is going to be equal to rho Lg sine theta initially. Right? Let's say you have placed the rope on a frictionless plane. That time, what is the tension? Suppose that it was frictionless. Tension was this, right? And now you turn on friction. You turn on the friction now. Even if you turn on friction, right now the rope has no tendency to slip because the tension is clearly balancing the downward force. So since it has no tendency to slip, friction that acts right now will be zero, right? So therefore, in this case, the tension would be rho Lg sine theta, that's it. It will not even have any other component, right? So basically, what we have seen is the values of tension at the top of the rope depend on how the rope is placed on the plane. And the tension at the top can take any value from a maximum of rho Lg sine theta plus mu rho Lg cos theta to a minimum of rho Lg sine theta minus mu rho Lg cos theta. And it can even take the value of rho Lg sine theta. All of these values are possible. Tension can vary from here to here. If the So this is for a rope basically, right? These are the minimum and the maximum values. If you replace the rope with a stick, which can actually support compressive forces also, then the tension can actually take negative values also, because it is possible that this value could be negative. This value could be negative. In this case, for a rope, it is possible that the tension is zero. Tension could be zero if this value rho Lg sine theta is less than this. Basically, the friction maximum force is greater than the gravity force, then in that case tension is zero. So 0 is a possible value, this is a possible value, this is a possible value, and this is a possible value also. Depends on how you bring the rope. This is the case when rope was stretched or dragged up or dragged down. This is the case where rope was already placed on frictionless incline and friction is turned on. Frictionless incline and mu is turned on. And this was the case in the standard situation when the rope was not stretched rope. And what was the tension at the top? This is the standard answer that you would expect. However, the tension at the top could also be zero. The maximum value of the value of mu rho g L cos theta is bigger than rho L g sin theta. Right? So you need to be aware of all of these cases, and it's not always that you will directly be able to predict the tension. It's not always super straightforward. Okay. Now that's about it for this particular class. I will share some more problems in the next session, and basically that will conclude our statics discussion. So I will do one more class with a few more problems, and hopefully that should conclude this particular section of the course. The next section in the course will be Newton's laws. So we'll do a lot of theory and problem solving. That's all for this video. If you like the content, please subscribe to the channel. I have created a bunch of courses on Udemy for students who are preparing for Maths Olympiads. You can check them out. I'm right now in the middle of creating an algebra course for Udemy, and that will be available pretty soon. So you can check that out also. If you need help, you should buy that course and see how we use problem solving techniques and discuss different types of theory and problem solving techniques for the exam. I'll see you next time for the physics course, and we'll continue in the next class.